All right, so number 9, PD9. So this Laplacian operator. So first thing I do is I set up just a little bit of notation. When you see this upside down triangle, and by the way, this is the thing that I was referring to when I said that you got to be real careful when you're writing down gradients, and make sure to write down the gradient with the point down, because if you put the point up like this, it means something different, and it's this thing, and it is a different thing, related but not the same. So we want to show that the Laplacian of this u function that's defined there in the statement of the problem, we want to show that this is equal to 0. In other words, now if you again look at what this Laplacian means, we just want to show that the second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to z, that adds up to 0. So this is just going to be some tedium, and I'm not going to compute all three of these, but I'll compute, let's say the first one, I'll compute the second partial with respect to x, and I'll let you do the others. Is that cool? Okay. All right. Okay, so let's remember, let's see, what is u? U is x squared plus y squared plus z squared, all to the negative 1/2. Okay, so first, what's the partial of u with respect to x? All right, chain rule, single variable chain rule, because u is a function of this inside, and the inside is a function of x. So what we've got here is negative 1/2 x squared plus y squared plus z squared to the negative 3/2, and now I got to multiply by the x partial of the inside, which is 2x. Right? Okay. So we have, let's see here, it is, we're going to have negative x times this business to the negative 3/2. Is that what you got?
Yeah.
Okay.
Okay.
Okay. All right, now let's do the second one. Let's see, second partial of u with respect to x. So we're going to take the x partial of this. We've got a product rule issue. Was that the issue? Did you forget to do the product rule?
Actually, I'm not sure.
Okay, well, let's see. Okay, no worries. I'll do it. So there is a product rule issue. So we're going to have first the derivative of, let's break this up like so. First the derivative of negative x, which is negative 1. And then x squared plus y squared plus z squared to the negative 3/2. And now I've got to take that negative x and multiply by the derivative of this with respect to x. Now again, be really careful here. It's a chain rule thing. So I'm going to have negative 3/2 x squared plus y squared plus z squared to the negative 5/2, and then times 2x. Again, the derivative of that inside. So altogether, I have negative that business to the negative 3/2. And then I have, let's see, well, now I've got a minus and a minus. That 2 cancels with that 2. I have, let's see, plus 3x squared times all this business to the negative 5/2. And I'm going to rewrite this for you a little bit. This is x squared plus y squared plus z squared in here. Let me rewrite this as follows. I'm going to write this as negative x squared plus y squared plus z squared times x squared plus y squared plus z squared to the negative 5/2. And then plus 3x squared times all that business to the negative 5/2. Because now I have a common factor of stuff to the negative 5/2, and then I can group these. I can group that and that together, and it gives me, let's see here, well, we have 3x squared and then minus all of this. So I have 2x squared minus y squared minus z squared, all times x squared plus y squared plus z squared to the negative 5/2. Okay, so that's this first second partial. Now, what's going to happen, so let me just say similarly, when you compute the second partial with respect to y, what you're going to get is something that looks a lot like this, except it's going to be negative x squared plus 2y squared minus z squared times all this. And then when you take the second partial with respect to z squared, you're going to get negative x squared minus y squared plus 2z squared times all that jazz. And when you add all, so this was the second partial with respect to x. When you add these three things up, common factor, and the x's cancel, the y's cancel, the z's cancel, and it all adds up to 0. Yeah. Now, obviously, I skipped much detail in these, but it's not unlike what we did up here. Yeah. Cool. All right. It's one of these kind of weird sort of calculations where it's just kind of strange that it all adds up to 0. So, for whatever it's worth, by the way, in physics, this is extremely important. This equation can be related to some important physics stuff about electric potential functions. And if you have, well, anyway, let me just say that this is related to potential functions in when you're talking about electromagnetism kind of stuff. And so depending on the situation you're looking at, you might need to solve this equation, and knowing that this is a solution is extremely valuable in that process. Yeah. Okay. All righty.